Welcome to the part 5 of our current chapter, alternating current. Today we are going to discuss the passage of alternating current through an LCR series circuit, which is also known as the acceptor circuit. So here we have a resistance, inductance and a capacitor, all in series, connected with an alternating source of EMF E equal to E naught sin omega t. The current running in the circuit is I. When this current will be running through the circuit, it will develop some potential difference across each component. Let the potential difference across the resistance is VR, across inductor it is VL, and for capacitor it is equal to VC. Now the EMF applied is E is equal to E naught sin omega t. We have already discussed the passage of AC through each of the components individually. We know that for the resistance, voltage and current are in phase with each other. So phase angle between them is 0. For inductor, voltage is leading the current by a phase angle of pi by 2 radian. But for capacitor, current is leading the voltage by the same angle, that is pi by 2. Now, this thing we can represent also on a phasor diagram for all the three elements for the LCR series circuit. This can be done like this. First we do it for the resistance. We know that for resistance, voltage and current are in phase with each other. So if we represent our voltage of the resistance along x-axis like this, then current will also be present along the same axis, because for resistance they are in phase with each other. For inductor, voltage is ahead of the current by a phase angle pi by 2. So let voltage is across the inductor is represented along the plus y axis. And for capacitor, current is leading the voltage by phase angle pi by 2. So voltage across the capacitor we can represent it along the negative y axis. So you can see here that for inductor, the phase angle is plus pi by 2 for voltage leading the current, but for capacitor, phase angle is plus pi by 2 for current leading the voltage. Now, if we assume that value of VL is greater than VC, if value of VL is greater than VC, then value of VL minus VC, it will be greater than 0. So difference of the two voltages will be greater than 0. This means that their resultant potential difference for inductor and capacitor, it will be along the y-axis. That we can represent like this. Let from O to this point we have the resultant potential difference VL minus VC for the inductor and capacitor along the plus y-axis. Now on this phasor diagram we have all the two phases main. One, voltage for resistance along x-axis. Second, the difference of the voltage of the capacitor and inductor, VL minus VC along the plus y-axis, and both of them are acting at the point O. So in order to find out the resultant of the two, we complete the phasor diagram by completing the parallelogram, in which we have a parallelogram OA-BC, in which side OA and CB represents the voltage for resistance, side OC and AB represents the VL minus VC. So in this case, the resultant potential difference of the LCR series circuit, it will be indicated by the diagonal of the parallelogram passing from the point O like this. So this will be the resultant value of the voltage. and you can see that the resultant value of voltage is inclined at certain angle with respect to the current axis, that is x-axis. So if we denote this angle as phi, from figure we clearly see that voltage is leading the current by a phase angle of phi. Now we want to find out first the value of this resultant voltage. So in order to apply find this resultant voltage, we in triangle OAB we use Pythagoras theorem, which says that OB square is equal to OA square plus AB square, that is V square is equal to VR square plus VL minus VC whole square. Now VR is a voltage across the resistance, which will be equal to I square R square, and for second term we have I into XL minus I into XC whole square. I is common, it can be taken outside. We have V square equal to I square into R square plus XL minus XC whole square whole under the root, or sorry, whole square, or V will be equal to I into R square plus XL minus XC whole square under the root. We can write down this equation as V is equal to I into Z, where Z is equal to R square plus XL minus XC whole square under the root. We can also express in terms of L and C as R square plus L omega minus 1 over omega C whole square under the root. So this Z is nothing but the effective resistance of the LCR series circuit, which we also call as the impedance of the LCR series circuit. So this voltage in case of LCR series circuit, it will lead the electric current through the circuit by a certain phase angle phi, provided only this condition is satisfied. This condition means if we assume that VL is greater than VC. If we go for the opposite side and suppose that VC is greater than VL, if VC is greater than VL, in that case VC minus VL difference will be lying towards the minus y axis. In that case, the resultant voltage V, which is lying in the xy plane in the first quadrant, it will lie into the fourth quadrant in the negative xy plane, that is over here, where current will be leading the voltage by the certain phase angle. Now this relation between the resistance, inductance and the capacitive reactance, inductive reactance, capacitive reactance and resistance can also be shown by a separate triangle like this, where along the x-axis we will represent our ohmic resistance, this will represent our difference of inductive and capacitive reactance, and this will be our resultant impedance for triangle A, B and C, and phi will be our phase angle by which voltage is leading the current. Now we want to find out the phase angle between the current and the voltage. In order to find the phase angle between the current and the voltage, we again take a look at triangle OAB. In triangle OAB, tan phi is equal to AB over OA, that is VL minus VC over VR, which will be equal to I into XL minus I into XC divided by I into R. I is common in numerator, denominator gets cancelled. So tan phi is equal to XL minus XC divided by R. This equation gives us the value of the phase angle between the voltage and the current. So we have already shown this in the impedance triangle. This is the impedance triangle. In this impedance triangle, if you want to find out the value of cos phi, the value of the cos phi, it will be equal to R by Z. Now discussion of the result. If we assume that if XL is greater than XC, if we assume that XL is greater than XC, if you look at this phase angle relation, tan phi equal to XL minus XC over R, value of XL minus XC, it will be positive. It will be positive. It will give us a positive value of the phi. This means that voltage will be leading the current by the phase angle phi. So circuit in this case, it will be purely inductive circuit. So LCR series circuit, although all three components are present, but because voltage will be leading the current by the phase angle phi, so circuit will act as a inductive circuit. So in this case, the current will be I equal to I naught sine of omega t minus phi. But if we go for opposite side, if we assume that XL is less than XC, then current will be ahead of the voltage. So in this case, circuit will behave as a capacitive circuit. And in this case, current will be I equal to I naught sine of omega t plus phi. But if XL somehow becomes equal to XC, inductive and capacitive reactors are equal to each other. In that case, XL minus XC will be equal to 0. Phi will also be equal to 0. This means that current and voltage will have 0 phase angle. That means they will be having the same phase. In that case, the circuit will become a resistive circuit. And when the circuit becomes a resistive circuit, in this case the impedance of the circuit will be, we know that Z is equal to R square plus XL minus XC whole square whole under the root. But if XL and XC are equal, the difference will be equal to 0. So Z become purely equal to R. So in this case, whatever resistance is offered to the current, it is only because of ohmic resistance capital R present in the circuit. So circuit is a resistive circuit in which the current flowing through the circuit, it will be I will be equal to V by Z, which will be equal to VIR, and it will be the maximum current flowing through the circuit, because normally we have seen that what is the current flowing through the circuit. So the current flowing through the circuit was I was equal to V by Z, where Z is equal to square root of R square plus XL minus XC whole square. But when XL and XC become equal to each other, then reactance effects disappear, circuit becomes purely ohmic in nature. So current in the circuit increases and reaches maximum value because resistance of the circuit is reduced to minimum value equal to the ohmic resistance. So in this case, current will be simply I equal to V over R. Thank you.